So it's my pleasure to introduce Professor Susan Athey, who is the Economics of Technology professor at the Stanford Graduate School of Business. She previously taught at economics departments at MIT, Stanford, and Harvard. And I actually had the pleasure of taking Professor Athey's market design course back when I was a student at Harvard and remember it very fondly as one of my favorite courses. So it's a pleasure for me to introduce her talk today. Professor Athey's current research focuses on the economics of digitization, marketplace design, and the intersection of econometrics and machine learning. She was one of the first tech economists and served as consulting chief economist for Microsoft for 6 years. She also serves as a long-term advisor to the British Columbia Ministry of Forests and has helped architect and implement their auction-based pricing system. She is the director of the Shared Prosperity and Innovation Initiative at Stanford GSB, and also associate director for the Stanford Institute for Human-Centered Artificial Intelligence. And today, Professor Athey will be presenting a talk on causal inference with longitudinal data.
Thanks so much for having me here at BayLearn. Today, I'm going to talk about some topics that arise in the design and analysis of experiments. So I want to start by presenting a paper that I've been working on about the use of surrogates. And this is joint work with Raj Chetty from Harvard, Hito Mbens from Stanford, and Hyun-Sung Kang from Wisconsin. Our motivation is that in many experiments, we'd like to estimate the long-term impacts of interventions. We might want to study some sort of social program, like changing class size, but we might also, in the digital environment, think about marketing experiments where we run ads and we're trying to understand the impact on long-term revenue. In fact, in most contexts where we're doing any kind of digital experimentation on a platform or a user interface, we're going to end up having a challenge waiting long enough to see how the interventions actually affect the things we care about. There's a couple of challenges that arise in estimating these kinds of long-term effects. Either we might just have to wait too long to see what the results are. And another problem is that experimental estimates are often very imprecise. And so the approach that we're going to suggest is going to address both of those issues. So to get started, let me talk about a couple of examples, the ones that actually got me interested working on this problem. The first problem I worked on actually back in the 90s, published in the early 2000s, and we were studying the impact of enhanced 911 adoption in Pennsylvania. And this was motivated by trying to understand the impact of technological progress on productivity. And so here we were trying to understand how getting basically caller ID for 911, how getting that installed was going to affect people's long-term health outcomes. But the problem is that there's a lot of noise and difficulty in actually estimating people's long-term outcomes after something like a heart attack. And so what we did instead is we took a look at measures that were observed in the ambulance, including things like the scores of your respiration or your heart rate. And we built an index based on those measures that we saw in the ambulance. And that index was basically your predicted mortality probability as a function of what we observed in the ambulance. Okay, so that was our setup. We observed some patients that lived in a place where they had an enhanced 911, some patients that lived in places where they didn't. We saw the data that was observed as soon as they came to the ambulance, and then we also potentially saw whether they died in the hospital. But of course, in general, we care not just maybe that they die in 1 day or they die in 3 days, but their overall long-term health. And so what we found was that when we measured the effect of enhanced 911 on your long-term health directly, we got pretty wide confidence intervals. And instead, when we constructed this intermediate metric, we'll call it a surrogate index, and studied the effect of enhanced 911 on that surrogate index, we got a similar magnitude estimate, but actually smaller confidence intervals. And at the time, I thought we were maybe doing something wrong, or maybe this was driven by functional form assumptions, because it didn't really make sense that we would get a more precise estimate of the impact of 911 on the long-term outcome by using actually an intermediate outcome rather than directly measuring the effect on mortality. And that puzzle actually stuck around for me for a good 20 years until Hito and I came back to this problem. I'd asked him about the time, and he didn't know the answer. And then we eventually discovered the insight that I wanted to show you today, which is that there actually can be efficiency of pooling data between the treatment and control groups and trying to understand the impact of and trying to understand the relationship between the things we observe in the ambulance and mortality. And so by pooling together all the people in the treated and control group and just learning what's the impact of what's the relationship between these short-term outcomes and long-term outcomes, we can actually get a more precise estimate. A second application I've been working on is in the context of a study of Uber drivers. And in this case, we're using telemetry from the mobile phone, and we're trying to understand the effect of something like an informational nudge for the drivers on the driver's safety. Now, again, we have a sample of data. It's not enough for us to look directly at something like accidents. And also, actually, your riders don't necessarily want you to drive in a way that completely minimizes accidents. Sometimes you want to get to the airport and you're willing to take some risk. So instead, what we do is we construct a measure of the quality of the ride based on star ratings. But of course, not every ride is rated, and one of the things we show in the paper is that some riders systematically give higher ratings than others. So for this and other reasons, we don't want to just look directly at star ratings since they're missing and potentially in a non-random way. So instead what we do is we build a model that relates the telemetry we observe in the phone to the star ratings. And then with that, what we call a surrogate index, we use that to evaluate the results of the experiment, and we show that giving drivers information about the quality of their driving, especially showing them if they drive worse than average, induces poor drivers to improve their driving. So now let me show you a little bit more about the approach we take in the paper. When we think about this using short-term outcomes as proxies, an intuitive solution, again, is to regress the long-term outcomes, say, if we're using an experiment on class size, regress lifetime earnings on, say, test scores of your or maybe your earnings in an earlier stage. Once we have that model of how these short-term measures affect the long-term measure, then we use that as an outcome to evaluate an experiment. Prentice in 1989 formalized this approach in biostatistics and called this a surrogate if two conditions were met. The first condition is that there's no effect of W on Y of the treatment on the long-term outcome that doesn't go through the surrogates. And the second condition is that there's no unobserved confounder that affects the levels of both S and Y that's also affected by the treatment. So that would say that the treatment doesn't change the relationship between the surrogates and the final outcome. Now, the problem is the validity of these assumptions are unclear. There might be some positive or negative effects of the treatment that are missed by the surrogates, and it's also the case that the treatment might change the relationship between S and Y. So an example of that is if your surrogate was clicks and your Y was long-term revenue, a treatment that put up a slideshow that lots of people click on might change the relationship between the surrogates and the final outcome. So if we're trying to combine multiple short-term proxies, we then have the questions of how can we estimate these long-term treatment effects if we don't necessarily have a valid surrogate? The approach we suggest here is that rather than debating whether any one variable is a valid statistical surrogate, we should create this type of surrogate index. The idea is that combining many variables might make it more likely that we span all the causal pathways from treatment to long-term outcome. But actually, when applied in settings like tech firms, we have to be very careful that we don't just throw the kitchen sink, because the assumption that W doesn't affect the relationship between the surrogates and the final outcome may be hard to justify when you have many surrogates. If you just take everything you observe about how a user is interacting with a web page, it's quite possible that the treatment might change the relationship between those interactions and final outcomes if you're not careful. So in our paper, what we do is we formalize the assumptions required for identification using a surrogate index, and we show that we can then use those for estimation using standard techniques. Something that we do that I think is fairly important is that we bound the bias that arises from violations from those assumptions, and we show how those can be validated. We also characterize the gains in precision from using the surrogate index instead of the long-term outcome directly, and then we apply this to show the practical value. So the application that we show in the paper, it comes from the California GAIN training program. This California Greater Avenues to Independence program tried to help welfare recipients find work. At the baseline, 22% were employed, and they had mean quarterly earnings of $452. Here we focus on what's called the Riverside program for Riverside County, and that emphasized a jobs-first approach to reentry in the labor force rather than human capital development or training. And the program offered job seekers skill assessments and tailored services to find jobs matching their current skill sets. There was a randomized trial to evaluate these impacts in the late 80s with 5,400 individuals. And the treatment effects are measured in a series of studies using data from unemployment insurance records. So when we look at what happens, we can look at just for the treatment group and the control group, what happens to their employment rates over time by quarter following the treatment. And so what we see is that the treated units do very well early on. Eventually, the control units end up looking like the treatment units, but there's a short-term impact, medium-term impact that lasts over many quarters. And if you go ahead and look at the average effect over time, there's a 6.37 increase in the employment rate for the treatment group overall this whole period. And one question is, could we have estimated the mean impact over 9 years more quickly using short-term employment rates as surrogates? And so again, the goal would be to get to the final estimate of this 6.37% number, but get there faster. And so what we do is we construct this surrogate index where we regress the final quarter employment on the previous quarter's employments from quarter 1 to quarter S, starting from the beginning. And then we're going to look at the quality of this prediction and its ability to be used to estimate treatment effects as we vary S. Then we estimate the treatment effects. So again, here's the goal to get to this 6.37% treatment effect number. If we form a surrogate index trying to predict that just based on the information we see in the first quarter, we would estimate a low treatment effect. As we add in the data from successive quarters, and each time we add in more data, we're able to better predict the long-term treatment effect. And we get there around quarter 5, and the estimates subsequently stay close to the truth. And so here we might say we think we can get the right answer with 5 or 6 quarters rather than waiting for 36 quarters to know whether this program worked. We can also see what happens if we make a naive short-run measure by just taking the mean over the certain number of quarters rather than actually building a predictive model of what's happening at the end. And so we see that building the predictive model gives us a better estimate than just taking the short-run estimates to date. Now, as I mentioned, we should worry that this whole surrogate approach may have challenges. And so here we provide a formula that bounds the bias in our estimates if any of the surrogacy assumptions are violated. And so one of the interesting things that we find is that the bias can be the biggest if the surrogates are kind of in the middle between the treatment and the final outcome. If the surrogates are sort of close to the treatment in the sense that the surrogates would be a good predictor of the treatment, or if the surrogates were a really good predictor of the final outcome, then we can show that the bias is very small. But it's in these intermediate cases where the bias could be bigger, there's more room for things to kind of go around the surrogates. And so we see here, and we are able to do the bias all with observable quantities except for one quantity. The one quantity that we can't directly estimate from the data is the question of how well that treatment predicts final outcomes. And so then we look at what those bounds look like as a function of that number. So here I've shown it with an assumption that the R squared of the regression of the treatment, the final outcome on the treatment is 1%. And what we see is that although we can get to the right answer within 5 or 6 quarters, the bounds that we would come up with get narrower and narrower as we get closer to the end. And so we might want to wait a little longer if we're concerned about violations of our assumptions. If we allow that the treatment has a bigger impact on the final outcomes, the bounds are wider, but they still start getting very skinny as we get close to the end. Finally here, I'm showing two estimates of the impact of the treatment on the outcome. Here I'm looking at actually two different outcomes, the impact on wages and the impact on employment. And we show here that these green lines show that the 95% confidence interval for the 6-quarter surrogate index estimate is actually tighter than for what we get if we actually use all of the data until the end. And again, that comes from the fact that we're exploiting our surrogacy assumption. Our surrogacy assumption says that the treatment doesn't affect the relationship between the surrogates and the final outcome. And so it's more efficient to pool the treated and controlled data and estimate that overall relationship, and that gives us an efficiency improvement. Overall, what we might think is that in a particular category of applications, whether it's building an A/B testing platform or a bunch of scholars studying similar questions about education or class size, what we should try to do is build a library of surrogate indices that we verify using longer-term data, and then we can use those surrogates in short-term experiments without having to wait to validate them. Of course, we'll still need to be careful about the validity of assumptions and take a look at things like bounds. Next, I want to turn to talking about some work I've been doing about causal inference in panel data models or in longitudinal data. And I wanted to highlight some of this work because actually a lot of the work that's been done in the causal inference and machine learning intersection in recent years has focused on the case of cross-sectional data. And I think there's actually a lot more open questions in the setting where you have longitudinal data. So one line of work I've been doing looks at using matrix factorization for consumer choice settings. And we're focusing on settings where we might have data about people shopping in a supermarket or shopping online. And there's actually a long literature in economics and marketing that focuses on consumer choice one category at a time. You try to estimate how consumers respond to price changes so that you can use it for questions like, should you give a coupon, or what kind of discounts could you give? And in this setting, we bring together work from the variational Bayes approach to estimate and stochastic gradient descent in estimating models that have a lot of latent variables. We allow users to have preferences for a lot of latent characteristics of items, and we allow items to have this potentially large set of latent characteristics. Some of the innovations that we have in this setting are that we tune our models to really focus in on highlight causal effects. We want them to perform well at seeing what would happen if we change prices. And also we validate our models with held out sort of artificial experiments from the data or natural experiments. We also take these kinds of approaches to simpler settings, for example, where we might have a set of states and we're trying to evaluate the impact of implementing a policy like changing the minimum wage. And in a series of papers, we proposed using matrix completion to construct counterfactual outcomes. And we also have an approach we call synthetic difference in differences, where we build on ideas of double robustness from causal inference and combine outcome models, such as matrix completion, with weighting that focuses on similar units and time periods. Now, all of this is about analyzing data that's already been created. What I want to talk about next is optimal experimental design in a setting where we have staggered rollouts. So we want to design experiments in a way that anticipates future hypothesis testing. And in these settings, we're going to take the matrix completion approach for outcome modeling. So we're going to design an experiment anticipating that we would use some of these techniques I just mentioned to analyze the data once it emerges. So this is joint work with a postdoc, Roshan Zhang. This is actually her job market paper from finishing her PhD, and now she's sticking around for another year for a postdoc at Stanford, and my colleagues Mohsen Bayati and Hito Mbens. So the motivation here is that statistical power is often a fundamental challenge in running experiments, and it's going to be particularly problematic even in tech firms or digital experimentation environments in several important categories of settings. A first setting is that a setting where there might be contamination or network effects among users. And so if you treat one user, it's going to affect other users. So an example of this would be running an experiment that affects Uber drivers. We might want to run those experiments city by city instead of driver by driver or rider by rider, because if I change the behavior of some drivers, that'll change the outcomes for other drivers and thus change their incentives. This is also a problem I worked on when I used to work on search advertising. If we wanted to run experiments that affected advertisers, we would have to worry about the fact that advertisers were competing against each other, or that something that you do might make them run out of budget or change their behavior in other ways that have feedback effects. So it's common to, in e-commerce, to think about breaking up your data either into verticals or industries, sometimes to look across countries if you're an international firm, look across cities. And in those settings, we have these challenges because we have a relatively small number of units. And then another big problem is there's a lot of time shocks and time shocks that might hit different units differently. So it felt like when I would try to study search advertising, basically there's like a holiday every week, a holiday that affects some industry more than others. Labor Day is different for some types of back to school advertisers, but then Halloween is going to affect a different set of advertisers. And there's always different holidays happening. And so we worry about how to run experiments in this environment when we have a problem with the small sample size. So just as an example, if we have something like a pandemic or a flu, we might want to study the impact of rolling out different types of measures, something like face covers or hygiene programs. So we can imagine that we have different cities, and some of these things might have spillover effects. If we tell everybody to wear a mask, or we have a campaign telling everybody to wash their hands, there may be peer effects or network effects across cities, and so we might want to treat a city as a whole. So one thing we could do is just do a 50-50 randomization. We could randomize cities to the treatment or control group. And then another thing we could do is try to worry about leveraging time. And so we could take every city, but we could actually launch the intervention at different points in time. And one of the scenarios we're going to think about here is a scenario where it's hard to remove the treatment once implemented. So if we do a mask campaign, it's hard. If we turn off the mask campaign, it's not the same as if we never ran it to start with. So effectively, we can't turn it off. And so we need to just think about a one-way treatment. Of course, in reality, you could eventually, those effects would peter out. But from the assumption we'll make here is that you just can't turn it off. And so what we want to do is find the design that will maximize statistical power. So if we did a 50-50 mix, the problem with that would be that we might just randomly pick some cities where people's behavior is more compliant in general and other types of health measures, and so it might be that we spuriously find that the things work just because of the cities we chose to treat, and people might come back afterwards and worry about that or argue that the cities you chose were different in some way. We could also just do a before-after study, but then the problem with that is, well, what if other things are changing over time? What if public officials are making announcements that interfere with your experiment? So that might not work so well either. So a third option is, well, what if we watch everybody for one period and gather the data, and then in the next period just treat half the units? And that way we can learn about the city effects, and we can also learn about the treatment effects. So our question is, how do we actually do that? There's a little bit of related work, but actually it surprised me that relatively little attention had been paid to this problem in the past. And so our contribution is to study the optimal multi-period design under a general class of linear models and show how to use historical control data to find a better design. So we have a model here. This is the data generating process. The model is going to allow for observable characteristics of each unit, and it's also going to allow for a factor model, potentially a latent factor model with interactive effects, so that there's a vector of characteristics of each time period and a vector of characteristics of each unit that apply to the latent characteristics of the time periods. And what we want to do is estimate the treatment effect, and we want to do that by figuring out how to roll out the treatment to minimize the variance of our estimator of the treatment effect, assuming that we can't remove the treatment once we've implemented it. This is an integer programming problem. Our estimation that we're going to use for this would be to just use the best linear unbiased estimator to estimate tau, and that'll give us an explicit formula for the variance of tau hat in terms of this. So the first result, which is very intuitive, is that if the covariates, the latent factors of the units, take on finitely many values, then any design that has staggered rollouts where we're treating 2t minus 1 over 2 total t percent of the units at each time is an optimal solution to this minimization problem. And it's actually easier just to show what this looks like. As we go through time, we're going to treat more and more units, and we're just going to end up with a situation where half the units are treated, half the units are control, but we're rolling it out over time so that for each unit we have the ability to learn both the unit effects and we also have the ability to learn the time effects for each time. And here's what it looks like. Now, in terms of the strata, so far that was just if everybody was in one strata. If we have more stratas, then what we do is we just break up the data into stratas, and then we apply the same type of solution. So just as an example, if it turns out there are two different kinds of cities, some are dry and have a lot of humidity, and some don't have a lot of humidity, we can run these experiments separately in each of these strata. And a remark is this result holds whether or not the unit effects are known or latent. And if we don't have a finite number of U, we can use a clustering algorithm, something like k-means, in order to stratify the units. So then as an extension, we look at the case where there may be carryover treatment effects. So maybe as we might start running ad campaigns for masks in 1 month, and then as we continue to run them, the cumulative effect may grow over time. So we can model that by just saying that there's a treatment effect which depends on the number of periods consecutively you've been treated already. And so what we can do is compare this little L equals 0 is the case where there's just one constant treatment effect, and then we see what happens to the optimal treatment assignment as we increase the number of periods in which there's still carryover effects. So here we'll plot what the optimal treatment assignment policy looks like if there are 5 periods of carryover effects. And one of the interesting things we see is that initially we actually treat fewer units, so we have more control units, but then later on we start speeding up the treatment. And there again, if we want to ever learn about the 5 full periods of effects, we want to sort of start getting more people into the treatment bucket before we get to the end of the experiment, and then they end up in the same place. So this is sort of a nonlinear solution that maximizes the learnings we can obtain from this experiment. So another question we can ask is, and it's very common if you're going to run an experiment like this, that we might have some historical data, and so we might want to ask, how can we actually use historical data, and how can we try to assess how to stratify our experiment if we may have learned something about users from historical data. And so the steps of this are that we first pre-process our historical data, where we split the historical data into several matrices. Then we're going to use a minimax decision rule, where we run in a synthetic experiment on each matrix, and we're going to try to find the treatment assignment policy Z that minimizes the maximum across these of the tau hat minus the true tau, this robust measure. And then we're going to use a local search or simulated annealing to keep swapping rows to put the units into groups using simulated annealing until we find a solution, a grouping that gives us the most, the lowest variance estimates, or the best experiment. So then we apply this to data, and actually this comes out of a project we've been working on around treatments for COVID-19, but we've here just used historical data. And here we're looking at inpatient and outpatient claim records from early 2007 to mid-2017. In this case, the primary diagnosis is influenza, according to the ICD-9 diagnosis codes. And we have 21,000 patient admissions and about 10 million outpatient records for influenza. And then what we're going to do is imagine that we were designing an experiment to study the impact of things like advertisements for face covers or other hygiene programs. And we're going to imagine that we're designing that experiment to reduce flu inpatient and outpatient flu visit growth rate. So again, we didn't actually run an experiment, but we're putting ourselves in the position of researchers who would be designing such an experiment and trying to determine how to design it to learn as much as possible using historical data. And so we're going to take this data, we're going to aggregate it at the MSA level, again, because we think that there may be network effects or spillover effects in month. We're going to focus on the flu peak season from October to April, and our outcome will be the log difference of 2 consecutive months of influenza visits. And again, we have a small number of units and small treatment effects, so statistical power would be a concern. So again, we might compare design matrices like 50-50, some studies treated, some control throughout the period. We could study, what would happen if we put the intervention in partway through the flu season, so we could see the baseline for all the cities. We have the 50-50 plus before and after design, where we first get a baseline in the beginning, and then partway through the season, we put in the program, and then this is what's recommended by our algorithm, which is staggered rollouts. And then we would be, so we'll start with just a simple thing before we do stratification. And so what we're plotting here in this artificial experiment, we're imagining that there's a treatment effect of negative 0.1, and we look at so using the real data, but just imposing this constant treatment effect, we assess the ability of different designs to estimate that treatment effect. And we see that our optimal design performs better in terms of getting smaller error bars. And that's going to be true across 3 different ways of estimating the outcome model, just simple OLS, a factor model, or a low-rank matrix estimation. We have 50 MSAs and 7 months. And so that shows us that the designing experiment is good, but actually it turns out that just the 50-50 before after, just treating half the units in the middle of the season would do about as well. But then we bring in historical data, and we try to see what's the benefit of trying to further optimize the experiment using historical data to stratify our experiment. And here we see there are definitely effects. We get smaller error bars from our optimal procedure, the Z-opt, and we see that those gains are largest in the low-rank matrix estimation. So what we're finding is that this nonlinear treatment design outperforms linear staggered design in addition when the treatment has carryover effects. So this final result is considering the case where several months of mask ads might have a larger effect. And so we're studying here the impact of our ability to estimate these treatment effects in the environment where we do have these carryover effects. And remember that our optimal design here was more complex. It had this sort of S-curve rollout. And we see that we get the best performance from using a design that's going to actually, optimize for that. And so that's going to be our best performing approach. So in conclusion, we've studied optimal multi-period design of experiments, and we've tried to understand what's the role of staggered rollouts. It's something that I've recommended to companies and policymakers for many years, but actually when I had designed these in the past, we had done it just with simulations or heuristics. And so this paper has a much more formal analysis of this, and it shows some non-obvious results, especially once we end up with carryover effects. And our synthetic experiments show how doing a good job with design can really make a difference in terms of power in several real-world data sets. We also, in the paper, look at things like retail and for further real-world data set examples. So in conclusion, using the theory and is going to help us design better experiments, and it also may be actually easier to design experiments using this kind of theory than just to try to do ad hoc simulations or back of the envelope calculations.
Thank you so much for that presentation, Susan. And now we have a bunch of questions to go through. So we'll start off with Mark's question here. Can we use surrogate indices in this way for prediction of a long-term outcome rather than estimation? And do different assumptions or methods apply?
To start with, the question we posed was, how do you analyze experiments, which really involves comparing a prediction of the long-term outcome from the control group to a prediction of the long-term outcome for the treatment group. And we're actually assuming in our setup that we have a randomized experiment at the start. So if you were just concerned with prediction by itself, that's in some sense an easier problem, but it's not really substantially different. So a lot of the similar considerations would apply, but I guess some of the oomph of the paper was about, getting more efficiency from in evaluating experiments from pooling the treatment and control group and mapping the surrogate to the long-term outcomes. I should have also mentioned, though, that another type of setting you might have with experiments is not just that you're worried about weighting, but there might also be some other kinds of auxiliary data you can bring in. And then you might have a much larger, data set in the observational data set than the experimental data set, which also brings efficiency gains. But generally, yes, you can also use this for prediction. It's just maybe, a little more obvious that you can do it, although a lot of the same concerns, come into play. But really, the focus of our paper was like, do the surrogates capture all of a treatment effect, or does a treatment change the relationship of a surrogate with a final outcome? And those things don't necessarily come up in a straight prediction problem. At least they don't come up in a prediction problem in a stable environment.
And then the next question we have is, does building surrogates also work when circumstances change, such as when a new program is introduced after a couple of quarters for an employment training program?
So this is a really big problem. And actually, I didn't talk as much about the work I've done with surrogates in tech companies, but one of the big challenges you have in tech companies is everything is changing all the time. And so when I've tried to design operational surrogates in tech companies, you have to really think hard about, what is it where I'm really sure that all the things I'm changing every day aren't going to change the relationship between the surrogate and the final outcome. So, there are many things you might change in the user interface, which could change the interpretation of various movements on the page. Something that might have a more stable relationship might be, say, like, dwell time or how much you spend engaging with the content. But various other aspects may or may not. And it really, of course, depends on your environment. In search, it might be the case that you're actually updating your relevance algorithms and stuff all the time. So the meaning of a score that's itself the product of a machine learning algorithm, you might have lots of scores floating around in your system, but those scores might change all the time. So again, seeing a score may not be a stable thing. So I think in general, the stability is a pretty big problem. And by far the biggest limitation of using these methods for surrogates. So one of the tactical ideas that I've had to get around that is, instead of trying to have one size fits all, which may frankly be impossible, you might want to think about different categories of interventions or different categories of experiments. So, if I'm going to think about throwing in slideshows, I definitely don't want to use clicks, but there might be a bunch of ways I might move around the things on a web page that don't involve slideshows. And so then I could use a bigger set of surrogates. And, the question was also about, if there's additional, training programs coming in, and there, I think it would only work if the surrogates you use were sort of closer to the final outcome than these other interventions. But you would have to ask whether, a certain intervention actually does change the meaning of the surrogates. Another type of place this could go wrong is, like, if suppose you were doing an email campaign and offering a discount, and suppose that someone, in order to get the discount, you have to go to the web page. Well, you got to be pretty sure that your surrogate doesn't include, like, just going to the web page on the same day you got the email, because it's sort of mechanical, and everybody who claimed the discount would immediately get a huge spike in visiting a web page. So you need to make sure that the meaning of visiting the web page is different if I, like, specifically drove you to get there and paid you $5 to do it, versus if I did something that made you naturally wake up in the morning and say, hey, I want to go to this web page. So those are some of the many considerations around, what would lead the surrogates to be stable.
And then the next question we have is from Shaya, who asks, how do you evaluate the performance of a causal analysis, both from model standpoint and from field testing?
The particular papers I presented today, we, in both cases, assumed that we had a randomized experiment. So at that point, the things you might worry about is, well, did I implement my experiment correctly? Was there some way that, the groups were contaminating each other? So at some level, that's it. The the causal part is not the hard part. The hard part is the other assumptions. So what we would want to be validating is, does the short term predict the long term? And so the one thing that we did, and I think that this is also what I did in the tech firm, is that, when you first introduce your surrogates, you find a data set where you watch them all the way from beginning to end. And, an old experiment, and then where you watch people 5 years. So then you can say, well, what if I had used surrogates after 1 year and see if it really worked for the 5 years? And one of my colleagues, Dean Eccles at MIT, just did a really nice experiment, surrogate analysis with Boston Globe. And there he looked at giving discounts for newspaper subscriptions. And so they did exactly this. They ran an experiment. They waited to see the longer term outcomes, but they saw whether after 1 month, 2 months, or 3 months, they could have accurately predicted the long-term outcomes. So when you first set this up, you validate whether it works, and then only once you validated it would you then go out and actually operationalize it in an A/B testing platform where you go ahead and make quick decisions without waiting to see if they're right. I should say, though, more broadly, a lot of my work looks at causal inference and observational data. And there we put one of the big focuses of my work is exactly how can you sort of validate whether your causal approaches hold. A lot of times there's a theorem that says that your models, that you can't actually tell if they worked. Like if there's as part of your identification strategy is assumption about unobservables, they're unobservable. But there's actually a large literature in applied social sciences around supplementary analyses or ways to do bounds that try to assess what you do with these unobservables. Another thing I work on is heterogeneous treatment effects. And there, the problem is that in your test, even if you had a randomized experiment, in your test data, there's not a treatment effect stamped on everybody's forehead. So if I want to see how well did I do personalizing, that's still hard to look at a test set because each person in the test set was only in the treated group and the control group, but not both. So I don't know any individual's treatment effects. And there, in a lot of our papers, we try to show how you can assess using various forms of averaging how well you've done at personalization. So I have a paper about targeted price changes, targeting price discounts. And so we put people into groups according to how we predict that they'll respond to price changes. And then we hold out data when there was actual price changes, and we assess whether we've done a good job putting people in the correct buckets by seeing how in this test set, how the groups on average at the group level responded. But there has to be some averaging. And that's different than prediction, where for prediction, you see somebody's outcome observation by observation. So you can assess each individual without doing any averaging.
Following on for a moment to this point about the difference between prediction and causal inference, I'm curious about your thoughts in terms of how causal inference should best be deployed in the machine learning context. In recent years, I think especially in the fairness, accountability, and transparency space, we've seen growing interest in causal interpretations and being able to trace causal pathways for biases and such. So I'm both curious kind of generally what you think of the role in causal inference in machine learning, and also given that I think for most folks in the CS community, causal inference equates to structural causal models and directed acyclical graphs. Like, what do you think is the role of potential outcomes or frameworks more so from the social sciences for informing folks who are looking into causal inference?
Yeah, so a couple questions all put together. So let me remind me if I forget some of them along the way. Let me start with the last one. One thing that's I think can be very confusing to people is sometimes you say the word causal and they mean two completely different things. So first of all, the part of the literature, which I think is very interesting, where you might use data to discover causal relationships, is really interesting and important. It is very hard to do in most economic data sets. And so that's basically why people don't often do them. So, but if you have a physical structure or a biological structure, you might want to uncover what causes what. And, does a hormone being released cause a physical response, which then causes something else? In economics, if you think about like getting something like the census data, everything's often correlated with everything else. And actually, if you looked at the assumptions required to apply that theory to, say, demographic data, they're just, ridiculous. So while you could in principle apply it, it's not useful because given the way the data is generated, you won't learn anything useful. Because we don't have enough of the right kind of variation in the data. There's just not enough, independence assumptions, basically. There's not enough independence in the data. What social scientists often do is actually they're kind of coming at it from another perspective. They want to say, what is the magnitude of this treatment effect? And I might want to, and I already know that like education causes labor market outcomes. I don't need, to discover that, right? But what I don't know is how much and for whom. And the problem that we're often faced with is that maybe there's no ways to figure it out. And so then you try to look at something like finding an instrumental variable or regression discontinuity, and you've put a lot of your emphasis on focusing in on like one particular natural experiment or source of variation that gives you any hope of answering the question. So everybody agrees on the question. There's 20,000 papers trying to answer the same question. And the only difference between paper A and paper B is, do you have a credible way to estimate that? And what we found in the social sciences is that in practice, and there's no like magic god of causal inference that told you this, it's just in practice, almost all of the credible, convincing approaches fall into a couple of buckets. So those are instrumental variables, where you have something that is unrelated to the outcome, but that affects the treatment. So an example might be your draft lottery number doesn't determine whether you go to Vietnam, but it's correlated with whether you go to Vietnam. Because people found their way out of it, and people non-randomly found their way out of it. You had a bone spur, or you were rich and you were in college, that got you out of it non-randomly. But nonetheless, the draft lottery number is still uncorrelated with your other characteristics, and so you can use it as a natural experiment. And there's a big theory about how you do that. Regression discontinuity, where there was some eligibility criteria, and you look at people on either side of the line. There are things like just panel data where you make assumptions that certain things are constant over time for individuals. The unobservables are constant over time, and you can infer the unobservables in some way or estimate them. And unconfoundedness, which is just a situation where you observe all the things that affect the treatment and the outcome. So there's a set of these types of designs which both have theoretical justification and are commonly enough observed in practice that you see people credibly applying them. And so for that menu, and again, everybody would love to find another one, right? I mean, we would love it if you get a prize if you figure out another one, but people have been trying to find them for 30 years. And the fact is that these are the ones that most commonly you find, and that the research around that is incredibly detailed and nuanced. So we already know what the graph looks like. Everybody knows what the graph looks like. The question is, how do I estimate it well? What kind of biases could come up? If I try to do regression discontinuity, I want to use a local linear regression instead of, just a simple regression because of biases around estimation at the boundary. So there's a whole bunch of attention to that. Each one of these literatures has a very finely tuned and well-developed set of empirical tools around them. Sometimes there's new innovations. I've contributed to those new innovations as well, rarely. And most of the emphasis is on, do the assumptions apply? Are they plausible? Have I done supplementary analysis that really reassure you that whatever assumptions I was making are credible? And, robustness, sensitivity analysis, magnitudes, and so on. So I think that's it's not that like one way is right and one way is wrong. That's kind of a silly way to look at it. Instead, if you want to understand why people do what they do, look at what is the problem they're trying to solve. And if they're trying to convince you that increasing the minimum wage from $15 to $16, doesn't have a big impact, you're going to care really strongly about getting the details right. Somebody's going to make a decision based on getting the number right. This isn't about philosophy. So actually, there was another question at the beginning of that, though, about causal inference. Can you just remind me just in half a sentence and I'll remember?
I think you kind of answered it, but basically just how should machine learning practitioners ideally be thinking about including causal inference methods in their work?
Yeah, and so if you Google Susan Athey AEA machine learning, I have a video course. It's aimed at economists, but about putting together machine learning and causal inference. And there's a link on the website that I'm updating. I have a lot of tutorials and also some things that are aimed more at machine learning about a more general philosophy about that.